making me extremely nervous about a number of people here leading into this next exam. And I know the hypothesis testing is difficult. That's what we're going to be talking about today, and really trying to get a good understanding of what we're doing there. So where we left off last class was talking about kind of p-values, or how to find these p-values, which were essentially, once we had our test statistic, was for left-tailed test, the area to the left of our test statistic, right, excuse me, tailed test, area to the right of the test statistic, two-tailed test. We had to find the area that was, kind of more extreme than our test statistic, and then multiply it by 2. And that was kind of where we left off. We said once we had the p-value, we make rejection decisions based off of that p-value is less than alpha. Or essentially, we were setting this threshold alpha amount such that if we saw, the probability of the sample mean that we saw was less than this threshold amount set, we were okay rejecting the null. Okay? So we had some more formal kind of ways of writing this. Oops. But ultimately, that kind of leads us to, these are the following steps, right? Well, the first is we talked about we have to identify the null alternative hypothesis. That tells us if we have a left, right, or two-tailed test. We're going to set different levels of alpha. So step 2 here can actually be done kind of right before step 5. If we really wanted to, we can move it down that far. But usually it's going to be given to us. So usually it's the second thing that we can do is identify what level of alpha are we testing against. We then turn our sample mean into a test statistic, or a z statistic, because it's coming from the standard normal distribution. Using that z statistic, we can find the p-value, and then finally compare that p-value to alpha. So let's return to that example that we were working with on Friday. So what we had was, we wanted to test for whether or not, I'm going to have to switch my camera over here, see if we can do this without screwing things up too much. Oh, that's not what I want here. Let me see if this gets changed. There we go. All right, perfect. So we had this example, and we said, okay, what we want to test for is whether or not that true mean is less than 7%, which meant that we assume the opposite is true and stack the deck against ourselves, which is that it's greater than or equal to 7%. So if we look at the alternative hypothesis here, we have a less than sign. You can kind of think about here, we've got a less than or a left-tailed test. We took a sample of size 36. We found a sample mean of 4.5. And now let's assume that somehow we were given that population variance of 1. Okay? Can we reject the null at the 5% level? So here are alpha 0.05. Okay? So what we're going to do is think about if what I assume to be true is in fact true, I can test for whether or not that assumed true population mean of 7% is in fact true, right? Can I reject it, or do I fail to reject it? Because if I can reject 7%, I can reject any other value in this range using my sample mean that I found. So I saw a sample mean of 4.5. So the p-value was the probability that I saw a sample mean as far away from that assumed true mean as I did, or something even further that went against that null hypothesis. So that p-value is kind of that area in that left tail there. Well, how can I find that probability? Well, any normal distribution I can turn into a standard normal distribution by simply subtracting the mean and dividing by the standard deviation. So I can turn this sample mean into a z statistic or a test statistic, and then find the area to the right of that test statistic, which is a z value coming from a standard normal distribution. So I can find that using my tables. Now, how do I turn this into a z statistic? Well, there's 2 different ways. So one, we said you simply take the sample mean. Now, usually we subtract the true mean, but we have an assumed true mean here, so we'll subtract that. And then we'll divide by the square root of my population variance over my sample size. which this denominator really, we could have calculated as an intermediate step, which would have been to up here, just calculate the standard deviation of my sample means first, okay? So, if I did that, I have what? Square root of 1 over 36, okay? And then down here, my sample mean that I found was 4.5. Subtract the assumed true mean of 7, and then divide by what? Square root of 1 over 36. Okay. So now that I have my test statistic, I can look that value up in my standard normal table. So this one, we saw a sample mean below the assumed true mean, so we should have a z statistic or a test statistic that's negative. Because remember, test statistic is still a z value, so it's still telling you the number of standard deviations away from that assumed true mean, which if we have a value below it, it's the number of standard deviations below that assumed true mean. So, if we plug all those values in to our test statistic equation, we get about negative 15. Now, this should seem outrageous because if we go to, did that just go black? Okay. I was doing this in my last section too. It'll go to this blue screen for no apparent reason. I didn't even, all I was doing was switching files. So let me see, try to switch it back here. And let's go back here, let's see if this works. There we go. So if we looked at that test statistic of negative 15, well, my table only goes as low as negative 3.9. Well, if the area to the left of negative 3.9 is pretty much 0, the area to the left of a test statistic of negative 15 is just going to be even closer to 0. Right? So we essentially here have a p-value that's equal to 0. Well, that makes our life pretty easy because if we're testing against an alpha of 0.05, is a p-value of 0 less than 0.05? Well, clearly, 0 is less than any of these alphas we could choose. So we say we reject at the 5% significance level. I actually just want to put in here to think about significance level. Or, said differently, we can reject with kind of 95% confidence. Okay. Any questions on that one? All right. So let's try to work through one more example. So let's say I'm trying to establish whether or not the mean retirement age is greater than 67. So if I'm identifying, first step, identify my null and alternative hypothesis. I want to test for whether or not that mean is greater than 67. So I'll assume the opposite is true, which is that it's less than or equal to 67. So here I've got a greater than or kind of right-tailed test because now only sample means that I see that are above 67 or on the right-hand side of the distribution, those are the only sample means for which I could potentially reject the null. So only the right tail kind of matters if you want to think about it that way. Now let's write these down so we have them. So sample mean we found was 71 out of 25 individuals. We're told the population variance based off maybe historical data is 81. And I didn't give you an alpha here because I'm going to show you something at the end that you can do. So all we're going to do is try to calculate the p-value and then think about, can I test against several alphas kind of quickly? Okay. So my setup now is, okay, what will the distribution of my sample means be? Well, if what I have assumed to be true is in fact true, then they should be distributed around that assumed true mean of 67. However, I see a sample mean of 71, so what's the probability that I saw something this far away from the assumed true mean, or even further from that assumed true mean, that goes against my null hypothesis, right? Because only values that are greater than 67 go against the null hypothesis. Now, I could calculate an intermediate step, which is the standard deviation of my sample means. That's just the square root of my population variance over my sample size, what, 25? So I think this ends up being, what, 9/5? And kind of where this came from. This is kind of the more general form. This is just something we've been using. Okay. So the next step, I need to turn that sample mean I found of 71 into a test statistic. And now with a right-tailed test, kind of find the area to the right. Okay? So I go ahead, what's my test statistic equation? Take my sample mean, subtract the assumed true mean. Now I can write this all in on one line, or remember this denominator was that intermediate value I found, which was the standard deviation of my sample means. Either way. So I'll take 71 minus 67 over the square root of 81 over 25. I think this ends up being approximately 2.22. Okay. So my test statistic here is 2.22. I want to find the area to the right of that. Okay. Any questions up to that, this point on it? So I've got my test statistic of 2.22. Let me know if this goes out again. This is where it went out last time. So I just come down here. The second decimal was 2, so let's keep going. 2.22. And the area to the left of that is 0.9868. So remember, the table is going to give me the area to the left. I wanted the area to the right, so just 1 minus that. Okay. So I looked up that z value, that z statistic of 2.22. I found the area to the left. For a right-tailed test, we have one more step, which is I want the area to the right, so I have to subtract the area to the left from 1. But now I've got my p-value. Okay. So now with that p-value, what I can do is I don't just have to test against one alpha. I could actually test against several alpha values relatively quickly. So we said that we only reject if the following is true. Is the p-value less than alpha? Okay. Well, my p-value is 0.0132. Is that less than 0.10? It sure is. So I can reject at the 10% significance level, right? Or I can reject with 90% confidence, right? So we kind of think about this as alpha. You can reject with 10% significance, or said differently, 90% confidence. I could then use that same p-value and say, well, do I reject at the 5% significance level or with 95% confidence? Well, my p-value is less than alpha, so sure enough, I can reject, right? With 5% significance or 95% confidence. Well, what about an alpha of 0.01? Well, it's not less than 0.01, so we'd say here, I fail to reject with 1% significance, or I fail to reject with 99% confidence. And sorry, this is a 5. This is a 9 down here. So the process, no matter what our alpha is, of finding the p-value is exactly the same. So once I have obtained that p-value, I can compare to several different alphas very quickly, right? In fact, another way to think about this p-value is basically it's the last alpha that I would fail to reject at, right? If I set an alpha of 0.0132, well, 0.0132 isn't less than 0.0132, right? It's the same thing. So that would be the last alpha value for which I would fail to reject. If I go to an alpha value even higher than 0.0132, I'll reject at every level above that. So it's kind of like my cutoff alpha value. You can almost think about it as. Any questions over this idea of kind of comparing to several alphas? Okay. Let's try going back here to the screen. There we go. Okay, so we have this all set up. We found our p-value. And then I kind of compare to different alphas, which I'll do again here in a second. But I want to work through one more example before we start to introduce some additional ideas. So let's say you've got this trade group and they state that the back to school spending average is $606.40. Okay? So you want to, you think that the average back to school amount differs from that, right? So right away, what you're wanting to test for, so you've got your alternative hypothesis, what you want to test for is, does that true mean differ from the reported amount of $606? Is it different than that amount, right? Or is it not equal to that amount? So you'll assume the opposite is true, which is that in fact, back to school spending is exactly equal to that amount. So anytime we see this word different than or differs, we should be thinking about we've got a two-tailed test. Okay? Now, we find a sample mean of $622. Your sample mean value should not be in your null and alternative hypothesis, right? Your sample mean is what you're using to try to reject certain values that you've assumed it to be equal to. So usually that null hypothesis value, that is assumed true value, is coming from some media publication or someone's, so you're making a statement that it's equal to a specific value, which is what they did here. So I want to see, does it differ from that amount? Okay. So I had 30 families. The sample mean I found is $622. I was given the population variance, maybe based off historical data. And once again, we won't specify alpha. We'll see how we can test against several alpha values pretty easily. So I've got what type of tailed test here? Well, I've got a two-tailed test. Okay. So that's going to make things a little bit more difficult for us. So what we're going to do is say, okay, what's the distribution of my sample means? Well, I've assumed that the true mean is $606.40. I found a sample mean of $622.85. So the probability that I saw something that was this far away from that assumed true mean or something even further is right here. But remember, the p-value is the probability I saw something this far away from that assumed true mean or even further that goes against the null hypothesis. Well, for every value in this range, there was a value that was equally as far away on the other side of the distribution, and those values now would also go against the null hypothesis. For a two-tailed test, either side, those values don't support the null. So I can think about if I find the area in this upper right tail, it's really only representing half my p-value. Okay? Now the process is still similar. I can turn that sample mean I found into a test statistic. Using that test statistic, I can find the area to the right, but if it's only half of the p-value, I need to take that area and multiply it by 2 to get my total p-value, right? So you can think about, I've got a two-tailed test. I kind of have an area on either side here. But it's really the same process. So I can go through, taking my test statistic equation, so I don't have to write it down and waste more space here, right? This is the format it's going to take. So the sample mean I found was what, $62.85. Assumed true mean was $606.40. And then my population variance was what, 4,225 divided by my sample size, excuse me, of 30. So now it's just a matter of getting this entered into my calculator. I think, no, this one is like I think it's 3.9. I can double check a second on the slides, but we find a test statistic of 1.39. So what I'm going to do is then look that value up in my standard normal tables. So 1.3 all the way over to the last column, so 1.39, 0.9177. So the table always gives me the area to the left, so 0.9177 is the total area to the left. I wanted the area to the right, so 1 minus that, but then multiplied by 2. If I do that, I get approximately 0.16. Okay? So my p-value is approximately Okay. Yeah, this is like a little bit unclear. Let me see if I can auto adjust this real quick. Maybe make it look a little better. I guess that's as good as we're going to get today. Any questions on that so far? So we've got our test statistic. We found our p-value. It's approximately 0.16. Okay. Let's go back here. We did all the work here. Oops. We ended up with, so exactly 0.1646. Okay. Now, if I use instead these alpha values, for each example, I could determine whether or not I reject or fail to reject. So we already talked about the first one a little bit, so let's focus on this second example we worked through. If alpha was 0.2, my p-value of 0.16 is less than that, so I can reject the null at the 20% significance level. However, that same p-value, it's not less than 0.1, so I fail to reject at the 10% significance level. And if I fail to reject at the 10% level, I'm definitely going to fail to reject at the 1% level, because if 0.16 is greater than 0.1, well, it's clearly going to be greater than 0.01. And the only way I reject is if my p-value is less than alpha. So kind of finding the p-value and then testing against several alphas is a way to really quickly perform like multiple hypothesis tests, because like finding the p-value is going to be the same approach no matter what my alpha is. Okay. Any questions on that before we kind of keep moving here? Okay, so I want to briefly introduce this idea, which is type 1 and type 2 errors. After the exam, I'll probably return to type 2 errors, but for today, I want to make sure we understand what type 1 errors are. So, oops. So we're doing this hypothesis testing, and I'm mentioning things like, well, we can do this with 90% confidence, right, or 99. So we're going to be wrong sometimes, right? So if we reject the null when we shouldn't have, that's a type 1 error. If we fail to reject the null when we in fact should have, that's a type 2 error. So we've got these type 1, type 2 errors. You can build a little table here, which is if the null is true, but I rejected it, that's a type 1 error. I rejected when I shouldn't have. If in fact the null is false and I failed to reject it, I should have rejected it, but I didn't, well, that's a type 2 error. And then the other combinations, are correct decisions, right? If I reject when it was false, well, I made the right decision. If I failed to reject when it was true, well, I made the right decision there as well. Different kind of combinations of the true states of nature and our rejection outcome. Now, type 1 errors we can think of as essentially alpha, okay? So why is that the case? I'll come back to that slide in just a second, but we'll use the example we did earlier, right here. Let me think about, yeah, we can use this guy, okay? So we use that first example that we did at the beginning of class and on Friday. So what we're doing with type 1 errors is saying, look, I know that if I set alpha at a certain level, so let's say I want the area in this tail to be a certain alpha value. Well, I know that anytime I see a test statistic, right, in this range, I'm going to end up with a p-value that's less than alpha, and I would reject the null. Right? However, let's assume for a second that what I assume to be true, this 7% as the true mean, let's assume that we go out, we get population data after we do this test, and we find the mean is exactly 7%. So if what we assume to be true was in fact true, then we know that for values out here, the probability of seeing them is low, but it is possible, right? So if we set a certain alpha value, we say, okay, look, anything that has a p-value less than 0.025, we're going to reject here. Well, if this ends up being the true mean, then any value we saw in this range, right, that, anything that led to a test statistic that was in this range, we're going to end up rejecting when we in fact shouldn't have, right? Now, the likelihood of seeing something in this range is low, right? It's less than the probability of 0.025, but we still could see it. And if we did, and this ended up being the true mean, we'd be making a type 1 error 0.025 or kind of 2.5% of the time. Or the probability we made a type 1 error would be whatever alpha is. Because for any value in this range, we're rejecting when we shouldn't have been. But for every value in this range, we'd fail to reject, and we shouldn't have, we should have been failing to reject. So we'll kind of be right 1 minus alpha. The probability we're right will be 1 minus alpha, and the probability we're wrong will be whatever we set alpha at. Okay? So alpha is our type 1 error. Excuse me. We usually call it this, and I kind of already referenced it, but the significance levels, which then makes 1 minus alpha the probability that we're not making a type 1 error. I always kind of like the example of, like, let's assume the null hypothesis is that someone is not pregnant. Well, here, if we rejected the null when clearly we shouldn't have, that's a type 1 error. Here, if we assume that they're not pregnant, and then we say, okay, we failed to reject that when we in fact very clearly should have, well, that's a type 2 error. Okay? So we got our type 1 and type 2 errors. Type 1 errors, essentially, we're setting, right? That's like kind of our threshold alpha that we were selecting or that was given to us. Okay? And I think maybe I can relate something to this type 1 error to the one more topic that we'll be discussing before we get out of here today. Okay? And like I said, I'll focus on this type 2 error stuff kind of after the exam. And then this is just a great meme. So I made a type 1 error. I shouldn't have rejected you, right? Because type 1 error is when you reject when you shouldn't. So I always liked that meme. So with that in mind, I'm going to introduce 2 new ideas this class, and we'll pick up on them on Wednesday. So we identified null alternative hypothesis for means. We can also do it for proportions. What ends up being true is we have the exact same types of tests, right? It's just now instead of an assumed true mean, I have an assumed true population proportion. Well, we have a greater than sign in the alternative hypothesis, so a greater than test, less than sign, less than test, or right and left-tailed, and then a not equal to sign, which is a not equal to or a two-tailed or two-sided test. So it's all the 3 same types of tests. We're just looking at a different statistic here. Okay? So the steps are going to be exactly the same. It's just our test statistic equation is going to be a little bit different. Just kind of like with confidence intervals, our confidence interval equation was a little bit different, but it's the same setup, it's the same steps or procedure. So one thing I wanted to point out here was when we built confidence intervals, we said the standard deviation of my sample proportions, oops, I forgot my square root, should be p times 1 minus p over n, right? But we said, well, look, with confidence intervals, we don't know what the population proportion is. So the best estimate we had was we had to use our sample proportions. Well, when I'm building this z statistic or this test statistic for sample proportions and an assumed true population proportion, notice this is pretty much what we were doing before. Before we took the sample mean minus the assumed true mean, sample proportion minus the assumed true proportion, then you divide by the standard deviation of the statistic you're looking at. So now it's dividing it by the standard deviation of my sample proportions. Now that is going to look similar to what we did. Remember, this was for confidence intervals, except now instead of needing to estimate the population proportion with our sample proportion, we have an assumed true population proportion. So that's what we're going to use to calculate that standard deviation. All right? So it's going to be a little bit different than confidence intervals when we find that standard deviation of our sample proportions. But once we know this is the equation we can use to find our test statistic, everything else is going to be exactly the same. Exactly the same steps as when we had a sample mean and we wanted to do a hypothesis test. Okay. Any questions on any of this so far? Okay. So the next thing that I want to talk about is, so eventually, once we get to examples, and like I said, we'll likely have to pick up with these on Wednesday, but I'll be showing you examples where we're looking at a sample proportion. But I'm also going to now show you the second method, which was before we said we had the p-value approach. The other approach we can use to do hypothesis testing is the critical value approach. So what a critical value is if we think about the standard normal distribution, the critical value is going to be the z-value that gives me my type 1 error in the tail, right? So the critical value is going to be a value, a z-value, that would give me the desired alpha or the desired type 1 error in my tail. Okay? Now you can imagine I could reverse engineer or work the inverse, and if I knew, the assumed true mean and the population variance, I could figure out the sample mean value that would be kind of correspond to whatever that critical value was. So if I see a sample mean anywhere in this range, it's going to lead to, actually I can use a different color here to help. So if I see a sample mean somewhere in this range, it's going to lead to a z statistic that's less than, sorry, I shouldn't say, it is less than, but I'm on the left side. So like it's larger in absolute value, right? It's a larger negative value. And then I know, okay, well, if I'm thinking about where's the p-value, well, remember, the p-value would be the area to the left. I know I'm writing this kind of small here. If you wanted to, you kind of draw an arrow down here. That shaded red area would be your p-value. Well, now notice, when I set that critical value threshold, anytime I see a test statistic that's more extreme than that critical value, it's always going to lead to a p-value that's less than alpha, right? Because as soon as I start moving to the left, well, now the area to the left is even more or less, even smaller, even further away from alpha. Okay? So really what we're doing was when we did the p-value approach, we said, is the p-value less than alpha, then we reject, right? So if my p-value, the area to the left of my test statistic, is less than the area to the left of my critical value, I reject. And that's also synonymous with the fact that, look, if the absolute value of my test statistic is greater than the absolute value of my critical value, I'll also reject. Now, it's a little bit tricky with the left tail test, which is why we take this absolute value, because really, like, it's a test statistic that's a larger negative value here, right? And if the test statistic is a larger negative value than my critical value, it's going to lead to a p-value that's smaller than alpha. So we're really just comparing two different sides of the same coin. We're just either comparing the areas in the tail, so p-value and alpha, or we're comparing the values on the x-axis that correspond to those areas in the tail, which would be my z-value and my test statistic. So another way of thinking about this, see how I'm writing this as like the critical value that gives me alpha in the tail? You could also think about your test statistic is what is going to give you your p-value in the tail, right? So I'm just either going to compare these two things for the p-value approach or these two things, I'm doing the critical value approach. Now the critical value approach is kind of nice because it gives you a visual. Once I determine, let's say I had an alpha of 0.025, I can use like that inverse idea, look up the area in the table of 0.025, find that corresponds to a critical value of negative 1.96. Well, now my rejection region is just going to be anything that's more extreme than that critical value. So now when I plot my test statistic, if it's anywhere in this range, I know that the test statistic in absolute value will be larger than my critical value. So anything in this range, I reject. If my test statistic ends up somewhere outside that range, well, this would be a scenario where I would then kind of fail to reject, right? It's not in my rejection region. Okay. So it doesn't matter if we use the p-value approach or the critical value approach, we'll always make the same decisions, right? And we only have to do one of them. Probably as I start working through these examples on Wednesday and Friday, I'll start to like do both at the same time, but we only ever have to do one to make that decision. Any questions at this point before we keep moving here? Where are we at in time? Oh, okay, we got plenty of time actually. Okay. So notice that when I'm dealing with a left tail test, which is how I set this one up, when I want alpha in the left tail, right, that's always going to lead to negative critical values because our alphas are small, right, 0.01, 0.025. So when our alphas in the tail are relatively small, I'm going to end up with negative critical values because think about what would the critical value be. Well, I'll draw this on a separate piece. What would the critical value be for an alpha of 0.5? We don't use 0.5 as an alpha because it's pretty high, but if I did have an alpha of 0.5, what would the critical value be? Standard normal distribution, the area to the left of the mean is 0.5, area to the left and the right of the mean. Well, the mean of our standard normal distribution is 0, right? So when we're dealing with alpha values that are a lot smaller than 0.5, all our critical values for a left-tailed test are going to be negative. Now, if I have a right-tailed test, I know that I want alpha in my upper right tail, which essentially means I would want 1 minus alpha to the left, which means that all my critical values for a right-tailed test are going to be positive, right, for my right-tailed test. So let's say I had an alpha of 0.025. What would the critical value be? Well, when I add an alpha of 0.025 for a left-tailed test, it's going to be the exact same value, but positive, right? Because it's a symmetric distribution around that mean of 0. So for left and right tail tests, we're going to end up finding the same critical values that correspond to those different alphas we use, typically 0.1, 0.05, and 0.01. Excuse me. So left and right tail will have the same value, but for a left tail test, they'll be negative. For a right tail test, those critical values will be positive. Okay. Any questions on that? All right. So here's our steps for these sample proportion examples. I think what I want to do, we've got 12 minutes left. So that critical value approach, we already kind of mentioned, once we find the value, if you draw kind of an arrow into the tail or like an area that's more extreme, we can think about that as my rejection region. So for a left and a right tail test, if I don't take the absolute value, for a left tail test, I'm actually thinking about a test statistic that is, less than. For a right tail, that would be greater. It's probably easier if we just write it like take the absolute value. If I take the absolute value of my test statistic and the absolute value of my critical value, the way in which we check rejection will always be the absolute value of the test statistic is greater than the absolute value of my critical value. But, if I draw it out, it becomes a little bit easier. I don't have to worry as much about kind of these, left-tailed, right-tailed, the sign flips, make sure I take the absolute value. So another thing that we're going to have to deal with is a two-tailed test. So a two-tailed test is going to be a little bit different. So let's think about what we're going to eventually want to do when we have these two-tailed test examples for critical values. So I've got my standard normal distribution. And normally I find the critical value that gives me alpha in one tail. The issue is, for a two-tailed test, I know that I actually want alpha total in the tails, right? So there's half of alpha on each tail. This starts to look really similar to what we did with confidence intervals. Because now if I want half of alpha in the tail, I actually know that the critical value that gives me an alpha total in the tails is going to be whatever value, a negative and a positive critical value, right? So I need the negative and positive critical value that corresponds to having alpha total in the tails. Right? Now, if you want to, you could write this a little bit differently, which is like, it's the critical value that gives me half of alpha in each tail, right? You have to remember that there's alpha total in the tails. So now it's just as easy as, well, now if I have, let's say my alpha was 0.1. Well, well, then I would want 0.05 in each tail. And I'm not going to kind of go through to go to the table. We've done this quite a bit. But if I go to the table, look up the area of 0.05, this should correspond to critical values of positive and negative 1.65. Okay. So the way in which I would write a two-tailed test, my critical value would be positive and negative 1.65, right? We actually have two critical values because before I do the test, if I see a sample mean that corresponds to a test statistic that's above the assumed true mean or below it, it doesn't matter, right? I could see one on either side that would go against the null or that would kind of be in this rejection region, right? Once I have my critical values, the rejection region was just anything more extreme than those critical values. Once again, it becomes important here. I can have negative test statistics and negative critical values. So what do I really want to do? Well, let's just say, let's make it easy. If the absolute value of my test statistic is greater than the absolute value of my critical value, then I'll reject. If not, I fail to reject. So once again, if we just always write it this way, critical value approach is a little bit easier. But now, in practice, like once I identify where these critical values are, and I take a sample, right? Maybe I see a sample mean, I don't, depends on what the example is, but I don't know, it's 750, okay? Oh, I dropped my marker. I then turn that into a test statistic. If my test statistic was somewhere like here, well, that's in my rejection region, I'd reject. Maybe I see 600, which corresponds to a Z statistic down here. Well, that's not in my rejection region, so here I would kind of fail to reject. That's the process that we're going to be using for the critical value approach. Okay. Any questions on that? Oh, make sure that if you didn't see that, this guy down here was there. Okay, so that kind of completes this slide for us. Now, one thing that's going to be nice is when we're using the same, basically all the problems we're going to do, we're going to use the same 3 alpha values. So we're always going to have the same critical values, right? Those same values that give us 0.1, 0.05, or 0.01 in the tails, always going to be the same. Now, for a left and a right tail test, I told you, same values, but for a left tail test, they're negative, right tail test, they're positive. For a two-tailed test, the values that correspond to these 3 alphas are going to be a little different because I now have 2 tails, right? And in each tail, I have half of alpha, so I have pairs of critical values for a two-tailed test. Okay. Questions on that before we keep going here? I might stop here. What was I saying here? So a lot of this is like things that I was just working through. So I'll probably review these a little at the beginning of Wednesday, but right, this corresponds to kind of everything we were just talking about here. We outline the steps where they really look pretty similar. It's just instead of finding a p-value and alpha, instead of using the test statistic to find the p-value and then comparing to alpha, we use alpha to find the critical value and then compare that to our test statistic. So it's a little bit different. We'll work through some problems where we've got sample proportions and we apply the critical value approach. So we'll do that Wednesday. I'll probably show you a little bit of stuff in Excel just to kind of help you envision how you would do that and maybe kind of help better our understanding. And I don't know if we'll move Wednesday into it, probably introduce the idea, but basically how do we do hypothesis testing when we've got sample means, but we don't have like a population variance, we only have a sample variance. It's going to be very similar, not a whole lot new. So we'll be able to cover all of the material for hypothesis testing this Wednesday and Friday. Tentatively, and I'll have the exacts of the exam to talk about on Wednesday, but it will be available 99%, with 99% confidence I can say. I'll have it open and available on next Monday and Tuesday, okay? So we'll do a little bit of review on Friday. I'll probably bring in some problems to work through on hypothesis testing. And then I might be filming a couple videos that are me working through some of the sample exams that are up there on Canvas right now under like the exam to practice material folder. So if you see some extra videos getting posted on that on YouTube, that's me working through some of those practice exam problems. But we'll also have time Monday kind of to do some last minute kind of work through some of the practice exam questions that you might still have on Monday's class before you take the exam. So I'll have more details about the number of questions and things like that on Wednesday. But for now, kind of the dates of that exam is going to be Monday and Tuesday of next week, kind of just like it was similar to the first exam. You can get on at any point in time, of about an hour and a half to complete it. Other than that, we've got a Excel assignment. I was trying to get back to my face to end this here. We've got an Excel assignment that's due Friday. So if you have any last minute questions on that, please send those to me this week. We can get that out of the way so that you can start kind of preparing for this exam. I'll also put up, it will look like a Connect assignment. It's not worth any points. It's just some hypothesis testing problems that if you want to kind of have some more things to work on this week as we're going through material, it'll just be up there if you want to take a look at it. I will post an online quiz that will have one question probably today that makes you work through a hypothesis testing example completely on your own, and maybe one or two other questions. Just kind of get at some of the concepts we're talking about with hypothesis testing so I can better understand what you guys are or aren't understanding to kind of direct Wednesday and Friday's classes accordingly. Okay? All right. Other than that, I will see you guys on Wednesday.